Okay, happy Friday. Welcome back. A couple of bookkeeping type things. First, the Gamma project is due. Throw it in the folder. I do take them late, but there are lateness penalties associated. So if it's not quite ready, you want to get it in as soon as possible. But if it's done, throw it in the folder for me. Today, project number 5 is officially assigned. So grab one of the projects and also grab one of each of the 4 kinds of candy, but do not eat the candy. Eating the candy makes it very difficult to do the volumes you're going to do on the project, right? So you should have 4 candies in front of you. Don't eat them. 4 different ones, as well as a project. Everybody has what they need? Okay. Last thing I wanted to say about the take-home quizzes, which I've handed back, is that you guys are working really hard, and it shows. And I just wanted to kind of compliment the group and say, comparison tests is a new kind of skill. Like, it's a proof-based skill, and for a lot of us, this will be the first time we're doing that kind of skill. And it is very clear to me that we are working hard, because the comparison test stuff looked great, and so did the other improper integral that you did, where you had to do a limit and a b and everything like that. And people are writing things very precisely and correctly, and I appreciate it. So nice job. Okay, so today we are continuing to talk about volumes. We'll do some more volume calculations, and lots of integrals is what we will see. Nothing else really on the horizon at the moment. No quizzes coming up for a long time. Test is still a ways away. So really only project 5 and homework is what we're working on now. Okay, so at the top of page 38, our daily summary. We now study a method of finding volumes of solids that are created by revolving a 2D region about a line. That line is called the axis of revolution. Let's take a look at the pictures here in number 1. It says, name the 3-dimensional objects that you get if you revolve the following shaded regions over the given axis of revolution. So we'll do these real quick, but you're going to take that rectangle and you're going to spin it, not just reflect it, but spin it all the way around that line. And so if we spin all the way around the line, circle there, everybody sees the cylinder? Right, it's just a new way to think of a cylinder. A solid cylinder, right? It's all filled in inside. Is just the thing that you get when you take a rectangle and you spin it around one of the rectangle's edges. All right, same idea here with the semicircle. What do you get when you rotate this guy around? Sphere. There it is. Look at it popping out of the board. 3D. You don't even need the 3D glasses. That's how awesome that drawing is. So we get a sphere, and then when you take a triangle, you get a cone. Yeah, right. We take this guy, spin it around, we get a cone. Super. And now we'll take a rectangle and we're going to revolve it around a line that's a little bit away, still parallel to one of the sides, but a little bit away. I don't really have a good name for this guy. Yeah, like a pretty thick pipe maybe. So we get that, and then this here, and that behind. Right, it's like it's a cylinder with the cylinder cut out of the middle, right? Yeah. Spacer. What is it? Spacer? Spacer or a bushing. Super. Okay, number 2 says, for each figure above, draw a slice perpendicular to the axis of revolution. So let's just do, we'll just do one of these guys here. Well, maybe 2. Let's do this guy right here. So we're going to draw a slice perpendicular to the axis, perpendicular to the line we're spinning around. Remember, our slice is just a little rectangle. And we're going to take that rectangle and let it spin all the way around. And so we let that rectangle spin all the way around. We get something that we might call a disc, right? It's a disc. No holes in the middle. That one is solid all the way through. I don't want to call it a circle because it's got a little bit of thickness, right? So disc. And if we do the same thing here, where there's a space in between, yeah, it's like a CD with a big hole in the middle, maybe a washer, right? Another kind of plumbing thing. Rob? Yeah. The disc part or the cone part? Yeah, this one right here. Right. So if you take a little rectangle that's perpendicular to the line that we're spinning it around, and you spin it around that line, and then this rectangle traces out what we're going to call a disc. It's just just spinning all around and creating that solid disk. Do you buy that? I can show you. Yeah? Okay. Right. So we'll just call that a disk. It's not really a hole so much. Here, I'll show you another visualization that maybe is a little bit better. Yeah, cross section is good. So watch this line right here. It's going to spin around this point, which is tethered to the axis of revolution. Where is it? Revolve. There we go. And so that blue thing, the dark blue thing, is just one of our rectangles. And we're just spinning it around, and we get this circle with a little bit of thickness, which we're going to call a disk. Okay? All right. So coming back here. Okay, that's good. And in number 3, we've got maybe things that aren't straight or perfect semicircles, but just curvy things. And if you take this first shape, which is the area under a curvy function, and you just draw your slice here, just like we normally do, that's our slice, and we spin it around, we still get a disk, right? It doesn't matter that it's a curvy kind of function that determines the space. It's still a disk when you spin a rectangle. And over here, this one is actually defined by 2 curves. There's this inner one here, and then the outer one is that guy. And if you draw, again, your slice perpendicular to the line you're spinning around, and you spin it, it's a disk with a hole in it. It's just a washer. And again, it doesn't matter how complicated the functions are. It's just disks and washers. Anything you spin, you can think of as being disks or washers. So, number 4, for obvious reasons, the method that we'll use to find the volumes of the solids from the last example is called the method of disks and washers. Okay, so I'm going to show you that sketchpad thing, but just one more piece of it. Let's go here, this guy. Okay, imagine taking this red region, it's between x equals a and x equals b, and we're going to revolve that whole region around the horizontal line. Again, that's called the axis of revolution. So you can imagine the solid that you'll get, and we're going to approximate the volume of that solid by rotating rectangles. I think we're going to have like 4 or 5 rectangles that we're going to rotate. And so if you take this rectangle and you spin it around, is that a disk or a washer? It's a very thick disk, right? This is a massive disk, so we'll revolve that rectangle around, and we get that guy, and that's that disk. And if you move x, you get another disk, and another disk, and another disk. So is the volume, all right, so volumes of disks are easy, right? Those are just cylinders, and there's an easy formula for the volume of any cylinder. So it's very easy for us to find the volumes of those 5 cylinders and add them up. Just like when we were estimating areas, we would add up areas of rectangles, right? How could I get a better approximation for the actual volume, which this is too big, right? Those things are a little bit higher. The rectangle's a little bit higher than the curve. So how do I get a better? More of them, right? Like make those disks thinner and have more of them. And it's very easy to have the computer or the calculator just give us as many as we feel like we need. So that's the idea of the method of disks. Washers is the same idea. So let's come here and do this crazy complicated example in 5. No, I think the fact that it was an overestimate had to do with the curve that was lying underneath. That red rectangle is slightly above the curve, and it doesn't matter how thick it is, right? Like this rectangle, this rectangle is always going to be above that curve. Yeah. This one, is it? Yeah, because it's a right-hand sum and the function is increasing. Yeah, that's what it is. But the error gets smaller if the rectangle gets thinner. All right, so number 5. Find the volume of the solid that is obtained when the region bounded by y equals the square root of x, x plus y equals -2, x equals 1, and x equals 4 is rotated about the line y equals 3. So we've got that set up and just a blank piece of paper in front of us. And drawing a good picture is a huge part of getting towards the right answer for this kind of problem. Some students try to like just jump right into an integral. Good luck. I have no idea what integral I would write down. I need to have a picture. I need to think about revolving things and getting disks or washers. Then I can set my stuff up. So let us try an integral here. A picture here. So we're just going to draw our picture. Y equals square root of x. I'm hoping that's just one that's in our toolbox, starting at the origin, going something like, I'm going to move my picture down a little bit. Okay, so starting at the origin, growing something like that, y equals square root of x. Next one is x plus y equals -2. What kind of a curve or graph is that? That's a line, right? It's linear. The x-intercept is -2. The y-intercept is also -2. And you can do like slopes and stuff if you want, but for me, it's just -2 there and -2 there. And my line connects those two. So that is x plus y equals -2. At the moment, there is no enclosed area. All of these problems have to have enclosed space, just like on the, not the Gamma project, but the one before where you found 4 areas. You guys remember doing this? Yeah. Every one of those pictures had to have enclosed area, right? And there's nothing enclosed at the moment. So we need more. So the next thing is x equals 1. What kind of a line is that? That's a vertical line. So we'll draw a vertical line at x equals 1. I don't know, black is good. Okay, so x equals 1, we'll say is here. I still don't have an enclosed space, but we're getting there. And then finally, x equals 4 is there. And now I think I can see an enclosed space. I'm going to shade it in temporarily, but can you guys see the region that's enclosed by those 4 things? It's left to right, below the blue, and above the red. Yep. That is the region we are revolving. We still haven't thought about this y equals 3, but that's okay. And the region you're revolving has nothing to do with the line you're spinning it around. You got to have a well-defined region, and once you've got that, then you can spin it around something. But they're really independent things. Y equals 3 is what kind of a line? Horizontal. Okay, so y equals 3, I haven't paid much attention to scale. I'm going to have a real problem if y equals 3 is that, because that goes through the region, and so I'm going to have like overlapping. You're not going to see any of those in this class, but it's worth trying to make sure that green really belongs above. So I guess what I want to know is how high is this point, because that's like the top point in my whole region. So at x equals 4, square root of 4 is 2, so that's a 2. So I'm convinced that y equals 3 is a little bit above that. Everybody see what we did there? I'll just label this point. This is the point. I know for sure x is 4, and it's on the blue curve, so I can plug 4 in there and get 2. So I'm convinced y equals 3 is just above something like that. Okay, so I've got my region. I'm going to spin it around that green line, and I'm going to get a 3-dimensional solid, and we're going to estimate, well, we're going to calculate the volume of that solid. Okay, we're going to draw a slice. Slicing is a word we're going to use every class for the next couple of weeks. We're going to draw a slice. For discs and washers, the slice has to be perpendicular to the line that you are spinning around. That's what we did in all the pictures on the previous page. So what kind of a slice am I drawing here? Is it horizontal or vertical? Vertical, because it's got to be perpendicular to the green axis of revolution. So let us draw something vertical here. Black is okay. And yeah, so I'm going to draw my slice here. It might end up being a little bit under the curve or a little over the curve. It's not super important. It's going to be thin enough that it won't matter. And I'm going to go ahead and call this guy right here X, just a generic. Let's give it a name. X is an appropriate name for that guy. X is just a name for where this generic slice is. And then I'm going to let this guy sweep left and right. X is just the name of that number. So what the goal is to find a formula for the area of taking this slice and spinning it around the green. And once I've got a formula for it, that's going to have X in it, right? Like, yeah, the location of that slice is X. And depending, like if you, all right, so let's come back to other Ben's question first. So if I take this guy and spin it around the green, what kind of a shape is it? A disc or a washer? It's a washer because it's got a hole in the middle, right? Like a really thin donut is good. So I'm going to find a formula for the area of this generic donut. If you move to the left, does that area get bigger or smaller? Smaller because there's just less space right, between these guys. And as you move to the right, I think that washer is getting bigger. So I'm just coming up with a formula for all of them, and it depends on where you are. So X is where you are. Okay, yeah, Rob. Yeah, it's this gap right here, which is why the hole is. Okay. Now you can draw more stuff. I'm going to draw some things and then erase it because it's just going to, I think, overly complicate the picture. But you can draw another copy of like this whole diagram flipped up here if that helps you visualize. But largely that rectangle exists, you know, like someplace up here, and then we're spinning and we've got that, and then up there. Oops, let's try again. And then up there we've got, you know, so like there's your washer, and we're just going to try to find the area of that washer right there. But the picture's already complicated enough, so I'm getting rid of that. Okay. All right, so let's do this. Volume of one slice equals. Okay, how would you find the area of the washer, just in English?
The volume of the first cylinder minus the volume of the cylinder of the area missing.
Yeah, we got a big thing, and we're going to subtract the stuff that's missing. And Yanni said the word cylinder. I'm going to say the word circle. It's going to have a little bit of thickness, so you are right. It is cylinder, but I'm envisioning a circle, and then we'll give it the thickness at the end. So area of the big circle minus area of the little circle. Let's write that. Area of big circle minus area of little circle. That's going to be an area, and then I'm going to give it a tiny bit of thickness to make it that cylinder. And how about delta X for the thickness? Maybe I can label it this way. That piece right there is delta X. And that's the volume of a cylinder. It's the area of a circle times the height. That's it. But it happens that we've got two circles that we have to subtract. Okay, so area big minus area of little. Okay, that's great. So then we come over here. So the area of the big circle, yeah, let's do that. So how much is the radius of the big circle? Radius of the big circle is here down to here. Yes? Depends. It changes. It depends on two things. It depends on the 3, the y equals 3, which is constant, but it also depends on the red diagonal line here. So I would say that this is y at the top, and this right down here is a y at the bottom. And if I subtract those y's, I'm getting the radius of the big circle. Got it? So that's what we're going to do. Y at the top minus y at the bottom to get that radius. And y at the top minus y at the bottom was a key idea in the first example in the activity from last class. You had two curves, and some of us were a little bit distracted by, I'll just show the picture again. Some of us were distracted by where the curves lived. Where is this? Here, this picture. And so, you know, the region is partly above the x-axis and partly below, but in the end we discovered it didn't matter where the region was. All you had to do was find the y at the top and subtract the y at the bottom, and that told you how high this thing was. Yes? So y at the top minus y at the bottom is going to be a standard refrain from us. So let's come back to the page we're on. Here we go. So area of the big circle. All right, so we need the y at the top. How much is the y at the top? Always 3. So 3 minus the y at the bottom. The y at the bottom is going to have an x in it, and that tells me I better solve this equation over here for y. I need the formula for the y. So solving that for y, you get -2 minus x. -2 minus x. Yeah, that's the y at the top minus the y at the bottom. And even if we can't see all the way to the end of this one, I'm liking the fact that this has only x, because remember we talked about how our expression had better have only the letter that follows the delta. Got to have only x's there, no y's. Okay, that thing right there, everything we've just written in that bottom line is the big radius, but we're looking for an area of a circle. So what's the formula for area of a circle? Pi r squared. So we need pi times that big radius squared. Pi times this guy squared. We will. Okay, and then we're doing minus now and back up to the top line here. We just calculated the area of the big circle. Now we need the area of the little circle, the missing circle. So let's do that one in black here. So this piece is the hole. That's the piece that's missing, and that's the piece I'm going to revolve around my green line. And I'm just going to find a smaller circle. So again, this area of that circle is pi r squared. So we just need to know the radius of that circle. How would you calculate the radius of that circle? Y top minus y bottom, green minus blue, right? It's the same y top minus y bottom. So how much is y at the top of that? It's 3, constantly 3. So 3 minus, and then at the bottom, how much is y? Square root of x. Good. That's the small radius. Again, it's pi r squared for the circle. So pi r squared there. And then brackets around everything and just see if you can squeeze a delta x, just copying it from before. Okay, so that's the volume of the one slice. And if we wanted to estimate or to find the volume of the whole 3D solid, we would just add up all those little volumes and then make the slices thinner and thinner. And lo and behold, that adding all of them becomes an integral, right? When we do this forever. And so let's write our integral. So the actual volume is integral. All of that, I'm going to be super lazy and just put blue brackets there. It's everything that was in the blue brackets before. I'm also being lazy there. I'll be clear on the directions, but if I asked you to do the summation thing, you would just stick a summation in the front of that. Put a summation thing in there. All I did was say, hey, we would add all of them up. If you wanted to write it, you would just slap a sigma in front of this blue line here, and then take a limit. We're just jumping to the integral. I'll be clear what I want you to do on tests or quizzes. Okay, delta x, what does it become? Delta x becomes a dx. And we're imagining sweeping this black slice left and right. From where to where? 1 to 4. That will give us the whole thing. Okay, and this integral is pretty straightforward. You want to do some algebra to clean it up first, right? Because there's squaring and foiling and distributing negatives, but there's nothing scary in there. It's just a big polynomial with some square root of x terms in it. You could split into 2 integrals. I think that some stuff will combine if you leave it in 1 integral. So I might hope for some cancellation, but you could certainly split into 2. So just to save time, I'm going to tell you the answer here, but there's nothing super interesting about it. 152 pi over 15. You can check that later, but it's going to be an easy integral. The hard part is what we did, setting all that stuff up. Okay, so 2 takeaways. Number 1, take your time when you draw the picture. Having a bad picture leads to bad calculus. Number 2, we've actually just got some simple formulas that we've essentially derived in doing this example. This example came out looking like pi times a big radius squared minus pi times a little radius squared. Every single washer example is exactly that formula. So here it is in number 7. The volume when you are doing washers is pi, I factored it out of both, times the big radius squared minus the little radius squared. That's inside of an integral. That's it. If it's just a disk, then you don't end up needing to subtract any missing stuff. It's just pi r squared. And so the only thing that I know about disks and washers is pi r squared. It's all pi r squared. Okay. There is an applet we'll just take a 10-second look at here. You can check out this webpage later if you want to play. Anybody heard this word? I don't even know how to say it. Lathe or lathe? Yep, we've seen this machine. Like you can like shape. Used it? Yep. So without any risk of damage to your hands or eyes, you can do a virtual lathe here. And so this is just making a solid of revolution by spinning this line segment over this line between the whites and the grays. And so if I draw another one down there, see it? Right, and so you can make whatever kind of spaceship things you want. Right. There you go. Lathe, no safety goggles required. So this guy's kind of cool because I think you can do like stuff that you can't do like with an actual piece of wood, right? Like, yeah, no problem. All right, so you can play around with that later. You can play? You can play? I don't think you can go below it. Yeah. All right, activities on the next page. Let me know if I can help.